Thermochemistry. Thermochemistry deals with energy changes that occur during reactions. There are two portions of the universe, the system and the surroundings. The system is the portion that we are studying, and the surroundings are everything else. Energy is the capacity to do work, but energy takes on many forms, and they are all capable of doing work. We have radiant, chemical, and thermal energy, but for thermochemistry, heat is the most important type of energy. Heat is symbolized with a Q. Heat is energy transferred directly from a hot object to a cold object. We can produce heat either from physical activity by increasing kinetic energy, which increases collisions, which will increase heat, or heat can be produced by the breaking of bonds when we form new substances. Energy can be classified as potential or kinetic. Potential energy is energy available by virtue of an object's position. For example, a rock on top of a hill has potential energy. Kinetic energy is energy of motion, and kinetic energy is 1/2 mass times velocity squared. We're going to look first at the first law of thermodynamics. The first law deals with heat and work. Heat can be positive when heat is absorbed by the system and the process is endothermic. Heat can be negative when it's lost to the surroundings and the process is exothermic. Just like with heat, work can be positive or negative. Work is positive when the surroundings do work on the system, and work is negative when the system does work on its surroundings. So here's a diagram. In these two diagrams, the gas is the system. So in the first diagram, the system is doing the work. The gas is expanding, it's doing the work, so work is negative. In the second diagram, the surroundings are doing the work. The system is being compressed. So since the surroundings are doing the work, work is positive in the second diagram. The first law says that energy can be changed from one form to another, but it cannot be created or destroyed. The first law in an equation form is represented by delta E equals Q plus W. Delta E is the change in internal energy. Q is heat and W is work. So let's look at a problem with the first law. Calculate delta E. So that is Q plus W. Q is heat, which is 4 kilojoules, but heat can be positive or negative. In this case, it says the heat is added to a quantity of air. So that means it's a positive value. Heat is added. Then the work is 0.5 kilojoules, but again, work can be positive or negative. It depends on what is doing the work. Well, in this case, the air expands and does work. Well, air is the system. So the system is doing work, which means the sign for work is negative 0.5. So heat is absorbed, positive 4. Work is done by the system. That's why it's negative 0.5. So the change in internal energy is simply 4 minus 0.5. So the change in internal energy is 3.5 kilojoules, delta E. Specific heat, symbolized by a small c, is the quantity of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Specific heat has units of joules per gram degree Celsius. And again, that is a lowercase c for specific heat. Heat capacity, the capital C, is the quantity of heat required to raise the temperature of a system by 1 degree Celsius. So heat capacity, capital C, the units for heat capacity are joules over degree Celsius. Specific heat of water is 4.184 joules per gram degree Celsius. anywhere in the range from 0 to 100 degrees Celsius. Let's look at a couple problems with thermochemistry. How much heat is required to raise the temperature of 735 grams of water from 21 to 98? So we're solving for Q, we're solving for heat. We're going to take the mass times the specific heat of water times delta T, which is the change in temperature. The mass, 735 grams. The specific heat of water is constant, 4.184 joules per gram degree Celsius. That'll cancel my grams out. Delta T is the final temperature, TF minus TI, initial temperature. So the change in temperature is 98 minus 21 degree Celsius. See how the units cancel out. We're going to end up with joules. So Q, the amount of heat required, (237,000 joules) is required for this process. We have a 150 gram sample of lead at 100. It's added to water at 22 degrees Celsius. The final temperature is 28.8. What is the specific heat of lead? In an insulated container, we're assuming that no heat is lost to the surroundings. So the heat lost by the lead equals the heat gained by the water. So MC delta T equals negative MC delta T. I'm just saying Q lost equals Q gained. So we'll start with the lead. The mass is 150 grams. We're solving for the specific heat, which is C. Delta T, TF minus TI. Well, TF is 28.8. TI for the lead, it started at 100. Set that equal to negative MC delta T for the water. So for water, plug in the mass, 50, specific heat, and then delta T, TF is 28.8, and we started at 22 for water. So we'll simplify this. We're going to get a negative on the left side over here. So negative 10,680 times C equals, will also come out negative on the right side. I'm just excluding units. But then C, when I take 1,423 divided by 10,680, the specific heat, which has to be positive, for lead comes out to 0.13, and then the units, joules per gram degree Celsius. So the heat lost by one substance has to equal heat gained by another substance, because we're assuming no heat is lost to the surroundings.